Welcome to a lesson with Dr. Powell. Let's take a look at an example of inverse functions and derivatives, but kind of in an application setting. Here's a very common one. We're traveling along, maybe miles traveled and time elapsed. So, the total number of miles we've traveled, even if we've gone back and forth and whatever else, will go up over time. It'll be an increasing function over time. It won't be decreasing, and we're not going back in time, but the total amount that we've traveled has gone up. This is a one-to-one relationship. It'll satisfy the horizontal line test, and so you'll have an inverse function. So miles traveled as a function of time elapsed from a given point will have an inverse. What will the inverse be? It will be time. What's the time at a certain mileage that you've traveled? Now it's going to be one-to-one as long as you're always moving. It's true. If you stop moving, then I guess it won't be a one-to-one relationship, because then you'll be like this, flattening out, right? You don't want that. So as long as we're always moving, so assuming there's no traffic jam, or we don't go to a stoplight or something like that, or maybe there is congestion, but we never actually stop as we go, and also assuming that we don't get off the freeway and go to a stoplight or something, I guess this would be a one-to-one relationship in that case. So we could think about an inverse function. So let's suppose in a given situation we're traveling, and maybe 3 hours have elapsed and we've traveled 150 miles. So on average that's like 50 miles every hour. But so depending on what kind of thing we're going through or whatever else, but assuming that we have this, so we've actually never stopped even once and moving along. Again, we're not going in places where you have stoplights or signs, so we're obeying traffic rules, but just for the situation. All right, so let's suppose at a particular moment in time you have at 3 hours we've traveled 150 miles. And the speed that we're traveling at instantaneously at that particular moment is 60 miles per hour. Is there a statement we can say about the inverse function, about time with respect to miles in terms of its instantaneous rate of change based upon this? Well, if you think about this, so it's T and M. So, right now we're thinking about a function which is like M as a function of time, right? So miles as a function of time. But could we go the other way? Could we say, so the inverse function would be like time of miles. And so this particular, so M of t, we're focusing on M of t when the input, t, is equal to 3. Now, if a similar statement, what would we want M to be at this point? Well, it would be 150, right? The input would be 150, which corresponds to that 3. Great. So at this moment in time, well, this one, what's M prime of 3, instantaneous rate of change, is 60. But now the question is, what is T prime of 150? What is that going to be? Should not. So if we think about it, we're swapping input and output. So we're swapping rise and run across from this input to that endpoint, but kind of based upon, these different, in these corresponding places. You should expect, rise over run to swap places, right? So when they swap places, won't our fraction here, 60 over 1, just be reciprocated? And it is, 1 over 60. So this would be, what would the units be? Well, time is hours. So 1 over 60 hours, per input mile. So 1 over 60 is the same thing as a minute. It's about a minute every mile. So every mile we go instantaneously at this moment, we'll add on an extra minute to our time elapsed instantaneously, which should make sense. This is just a simple example of noticing a common rule that we have when we're looking at inverse functions. I mean, we could just be using symbols here. I mean, we could have thought of this m prime of 3 as simply being dm dt at t is equal to 3, and that's equal to 60. Now we're considering right here, we're considering dt over dm when m is equal to 150. But notice the situation of m is equal to 150 is equivalent to the situation of t is equal to 3 here. Those two are the same ideas. It should notice that we took a reciprocal on these in this fraction. And it's going to be the reciprocal as well here. Now, if you interpret these symbols as simply being rises and runs on a tangent line to a curve, and that ratio is always going to be the same on that tangent line, because that tangent line is going to have the same slope. And if you think about it that way, it does correspond and it does reciprocate. I mean, you have the curve for m, right, and the tangent line right there. So you have dt and dm going up. Now when you swap your, well, here you're swapping your input and output, your t and m. The tangent line, so here, if you're thinking about, you know, where t is and m is here for your curve, so suppose, you know, I'll just kind of pretend like this is the line, m is equal to t, just for a second. So when you swap your x's and y's here, and maybe I'll erase that, so I'm just not thinking about that at the moment. But let's just kind of, for intuitive sake, think of what's happening here. All right, so you swap your t's and m's, so your picture reflects itself. And not only for that, but it also reflects itself for the tangent line. So across this, you know, you have a tangent line here. Maybe I'm not drawing it exactly right, but the idea is that this triangle reflects across, and this dt becomes, and this dt will, let's see, it reflects across, and this dt will be, you know, upward, and dm will be, so dt and dm. Notice how you get that reflection. So, you know, as it goes off to the tangent line, of course, if I get the reflection right. But the idea is that it reflects across, and you get, and dt over dm really does give you, in that reflection from that point, from the tangent lines, does give you a reciprocal. And so we have 1 over 60, and you can kind of see that intuitively in thinking of these as being a rise and run on tangent lines themselves. Not on the curve, but on the tangent line. That would be an appropriate way of thinking about those symbols. Hopefully this is a good little example of how to look at a situation like this. Really, the solution was given early on. I just gave some additional explanation here on this. But how would you find t prime of 150? Well, it's sitting right in front of you. You just take a reciprocal. That's really it. Just a simple idea. And we're done with that one. Thanks for watching.